Hi. Hi, I am not Carolyn Lawson. Hi, Carolyn. I'm Karen Powell. Carolyn's got to step out to take a phone call, so I'm stepping in and actually give me an excuse to come in here to listen to your talks. I've always enjoyed it. So I will be the session chair. Matthew here will be the timekeeper, and I think you have 20 minutes, 30 minutes, 20 minutes to give your talk. Speakers, 15 really, with 5 minutes. Well, if you see me standing there, doing stuff, that's when you gotta wrap it up, okay? All right. So without any further ado, our first speaker is Michael Rosario from Duke University. He is studying evolutionary biomechanics. His advisor is Sheila Patek. And he did his practicum at San Diego National Laboratories, California in 2013. And the title of his talk is, So Much Work, So Little Time, Maximizing Elastic Energy Within the Duration of Muscle Contraction. Michael.
Thank you very much. Thank you very much for the introduction and for having me here to talk about you. I'm really excited to shake it up a little bit and really just show you some really cool animals. By studying, I'm a comparative biomechanist, so I like to look at really cool animals and study the physics behind them. And so before we go into the talk, I'd like to break down the outline. I think this is really important to understand the structure, the way that I designed this talk. So we're going to start with elastic systems in biology. This is the introduction. We're going to learn about muscle spring systems, learn about why muscle spring systems are important. And I like to consider this my National Geographic portion of the talk. And then we're going to look at two variations of the same model, a static muscle spring model and a dynamic muscle spring model. And the reason I think it's important that this talk was divided into these steps are because this approach requires no parallelization. It might benefit, but it doesn't require it. Whereas once we go to the dynamic side, then that's where we see the parallelization happen. And so it's a really nice view of a before and after effect of the fellowship in terms of my training and being able to propel my research forward. But first, let's start with some cool animals. So here we have a mantis shrimp, a chameleon, and a flea. And what we like to do is look at these animals and try to find what's in common. And this is a really fun exercise. And so many people might know what a chameleon is. Many people might know what a flea is, but what is a mantis shrimp? In case you haven't noticed, they've gone viral in the past year or so with the oatmeal comic and whatnot. But these are little shrimp. Some can fit in your hand. Some of them get to as large as this. And what's really interesting is the reason they're called mantis shrimp are because they have these appendages sticking out in front of them like a praying mantis. So here's a mantis shrimp in the side view. There's a big appendage right here. There are the eyes. It's facing sideways. And there you can see forceps holding a snail shell. Now what's really interesting about mantis shrimp, this is a slowed down video by the way, is that the striking appendage swings forward and completely obliterates the snail at the point of impact. And so this striking appendage really is an amazing, powerful weapon. In fact, the acceleration of that strike matches that of the acceleration of a bullet out of the muzzle of a gun. Pretty amazing. And if any of you are interested in mantis shrimp, you can ask me about them later. We have a bunch of them in our lab. If you're ever at Duke University, you're welcome to stop by the aquarium and have them hit a little stick. It's a really fun thing to do. So here we have a veiled chameleon. This is another slow down video. And over here, there is a locust that is stuck to a piece of paper. And again, this is an amazingly fast and powerful tongue projection. And recently there was a paper that came out that showed that a chameleon that could fit in the size of your hand could generate the same amount of power as a commercial dirt bike, about 54 horsepower. And we'll just finish it off because everyone wants to see it, eat it. Yum. All right. And so we go on to the flea, and everyone knows that fleas jump. Right? This is a slowed down video of a flea jumping. But when you actually look at how high these things can jump, they reach, depending on the species, they reach heights from 200 to 400 times their body length. So they jump super high. And so the thing that all of these movements have in common to these animals are that they're necessary for their daily lives, right? That if the mantis shrimp can't break open that snail shell, it can't have dinner. If the chameleon can't move its tongue fast enough, it won't be able to reach that locus. And if the flea can't jump that high, you can't get on your dog, which is probably a good thing, but a bad thing for the flea, right? And so the thing that binds the diversity of everything that's up here together is in fact power. And when we look at these values of power, 470,000 watts per kilogram, 41,000 watts per kilogram, these are really high values for power. And as a demonstration, the most powerful muscle measured, that of a hummingbird, is only 120 watts per kilogram. There's a huge difference between the power that, in the movements that these animals generate and that of muscle alone. And the reason they're able to generate these extremely powerful movements are because they use not only a muscle, but a muscle connected to a spring. So the muscle contracts very slowly, it stretches the spring, elastic energy is stored in the spring, and now that energy in the spring can be used almost instantaneously to power these movements. As an analogy, if I asked you to stand on that side of the room and I gave you an arrow, you could throw it. It might go pretty far and it might go pretty fast, but if I gave you a bow, a spring, using the same amount of muscle power, you can generate an extremely different kind of movement. And so since these animals rely on elastic energy for their daily movements, and the elastic energy comes from the spring, one question that I'm particularly interested in is, are springs tuned to muscle in order to maximize the storage of elastic energy? So to answer this question, we're going to look at a very small snapshot, a very small slice of biological diversity, and focus mainly on a bullfrog. Bullfrogs or frogs in general have been shown to store elastic energy prior to jump in their hind limbs. And the reason also why this is important for us to understand is by understanding the spring system in the frog, we learn something else about the human leg, because these systems are very similar. There are some differences, but they're very, very similar in terms of having a muscle connected to a tendon. So that leads us to the formulation of a static spring muscle model. How do we model this? How do we get answers out of this and make predictions? So very simply, what we can do is connect the two muscles together through static equilibrium, right? So the force of the muscle equals the force of the spring, very simple. What we can do from here is break down these forces into their constituent models and then set them equal to each other, right? So the force of the spring is relatively easy. This is a linear approximation known as Hooke's law. You might remember this from your college physics or high school physics even. Where we have two components, K, which is the stiffness, and X of S, which is the amount that the spring stretches. So you can imagine, to get a really high string force, you'd want a really stiff spring and then to stretch it as far as you can, right? So the model for the muscle is a little bit more complicated than that. There are three components and this model is based on a physiological hypothesis of how muscles work. I won't be able to talk about that today, but I could draw little diagrams of actin and myosin if you're interested after the talk. But the three components that go into the force of the muscle are force due to activation. You can think about this as muscle effort, and the velocity and the length of the muscle. Those both interact to determine how much force the muscle can produce. Now, since we're interested in looking at elastic energy, the maximum amount of elastic energy, we're looking at a sort of static solution in which case these factors, the dynamic factors, don't contribute. And so we can ignore these by setting these to 1, since these are all multiplicative. And one more simplification that we can make to get our final static model is we notice that there's two x's here. And we know from our model that whatever distance the muscle contracts, the spring stretches that same distance, so we can make that simple substitution to get our static model. And so one of our collaborators, Dr. Greg Sutton from the University of Bristol, came up with a really great way to visualize this by basically plotting these out. So here is an example of a force length curve. At this point, the muscle is at rest, and as the muscle contracts, it can generate less and less force, and this line represents the maximum force that can be generated at that length. And so what we have here on this side is a line, right? And again, where the spring is at rest, and as the spring stretches, it generates more and more force. And so if we overlay these two, we can get a sense of the farthest distance the system can stretch and the force at that distance. And that's really all we need to solve for the elastic stored energy, which is equivalent to the area under this line. Right. So what did we do with this model? We basically took empirical data from a muscle of a bullfrog. We took the muscle, it was stimulated, and we figured out the maximum force it generated for various distances. And to that, we added springs of varying stiffnesses. So there's an intermediate type of spring. We added a more stiff spring, which you can also tell by the slope. We added a more compliant spring, again by the lower slope. And what we were interested in is which spring corresponds to the most amount of energy stored, or in this case, the greatest amount of area that can be created in the system. And so once we find that stiffness that generates the most amount of energy, we compare that to the actual measured stiffness of the bullfrog and see if those two match up. So what did we actually see using the static model? So on the y-axis here, we have energy. On the x-axis, we have stiffness. And again, as a reminder, systems over here have lower compliance, systems over here have higher stiffness, and they're all connected to the same muscle. And another data point that we're going to add here is that the frog actual measured tendon stiffness lies around 10 newtons per millimeter. So what we'd expect, if this question was true, if the stiffness of bullfrog tendon does maximize energy storage, we would see a peak right around 10 newtons per millimeter. But when we run the simulation, we find that the expected value is much higher. And so there's a discrepancy here. And the answer to this question is actually no. Right? The stiffness of bullfrog tendon doesn't maximize energy storage. If it were stiffer, it would store more energy. And now the interesting question to this is why? Why is there this discrepancy here? And there are two reasons why this could be true. One is simply that we've supported a null hypothesis, right? That the bullfrog muscles and tendons are not tuned to store maximal energy. But another alternatively valid a valid reason why this could happen is that the mathematical model is incorrect. And I got a lot of pushback from one of my collaborators, like, no, this mathematical model is correct. You know, we took a muscle and a spring, we broke it down, and we connected the forces. We were interested in maximum elastic energy, so we cut it off there. And so we went from a situation where we're at rest to full contraction. But the question that I was really interested in is, well, is this model appropriate for answering our question? And so when we look at a jumping bullfrog, it's a very dynamic movement. And when you take the muscle and you stimulate it, you find maximum contraction occurs at 100 milliseconds. But when you actually look at the bullfrog jumping, it only contracts its spring for 50 milliseconds. So here we see that there's another discrepancy between these numbers, which means that the muscle is not fully contracted prior to jump. And to really hammer that home, this is the model's endpoint at its current state, and this is the biological endpoint. So this really pushed us forward to go forward with the dynamic muscle spring model. And so the dynamic model is very similar. We set the forces equal, but now we can't ignore the velocity component or the activation component. And if we break up velocity into change in x over change in t, we see that this becomes complicated for us to solve because x of m has direct effects on force as well as indirect effects through velocity. And so what we had to do for every time step was solve the value find the value of x of m that satisfies this equation. And in order to do this, we isolated everything that had x of m to one side, and I wrote a numerical way to solve for this, and we run that through parallel because we had to do it through multiple iterations. We did the same thing, asked the same question with one change, which is that now we're looking for whether or not the stiffness of bullfrog tendon maximizes energy storage within 50 milliseconds, right? And this is the biological realistic time point. And what we found is actually, yeah, we get a lot closer. And so the reason I set up the talk this way is so we could look at this in a way that, that shows how this fellowship and this training has fundamentally changed the interpretation of the results. So first we looked at how different animals and elastic energy storage. We found that in the static case, bullfrog tendons don't maximize total elastic energy, but in the dynamic case they do. And I think this is a really neat opportunity to answer this, to look at this, to reflect on the use of role of high performance computing on your research, that injecting parallelism and the training that I got from this fellowship, we were able to generate a different model that asked the more biologically relevant question. right? And so what we're doing now is the same sort of thing, except now we can change on the y-axis different muscle parameters. So we can explore the entire space of different muscles, of different stiffnesses, and this is broadening it out a little bit so that we can actually study elastic systems throughout the diversity of life, and these are just some of my favorite examples of elastic energy systems throughout the tree of life. And with that, I'd like to acknowledge especially the DOE and Krell Institute. This is a picture we took our 0th year, I guess, with everyone. And the reason I put that up there is because all of you are amazing. I love being here. I don't think I've ever been in a room with as many smart people as I am every year when I'm here. So thank you very much for your support and training. I'd like to thank my collaborators. I've never found a room of people who are so interested in elastic systems than these 3 people right here. And actually, I included this picture because you can see Professor Greg Sawicki testing and collecting data on an exoskeleton he's built for his leg to maximize energy. I'd like to thank the members of my lab. We're all sort of moving on to different positions. And that I want to include myself in that, and I'm moving on to a postdoc with Dr. Tom Roberts, who really is excited about this research and supports it. He is at the forefront of muscle physiology, so it'll be really interesting for us to interface and talk more about these types of things. And I'd also like to thank the NSF for awarding me the biology postdoc fellowship to do this research. And with any time, if I have any time left, I'd like to take any questions.